And now we move on to the second page of this, problems 3 and 4. And we are doing stoichiometry, all types. On these problems, we are still working from our stoichiometry sheet. 9-19 is practicing problems where we are going places other than mass to mass. We already learned to go mass of one thing, use a chemical equation to bridge the gap from moles to find mass of something else. In 9-19, we're learning to go other places, somewhere on this side to somewhere on this side. On this chart, the given is in red. The thing we're trying to find is in green. And let's take a look at problem number 3. Problem number 3 has a nice little description, which leads us to this chemical equation right here. In this chemical equation, we have NO2 decomposing into N2 and O2. We have to balance that. If we have two O's here, and we're going to have a 2 after the N and a 2 after the O here because nitrogen and oxygen are both diatomic elements. So if we have to have a 2 here, we're going to need to put a 2 in front here. If we have diatomic nitrogen here, we need a 2 in front here. 2 times 1 is 2. 2 times 2 oxygens is 4, so we need a 2 in front of this. We now have our balanced chemical equation. In our first problem, they're asking us how many molecules of oxygen could we produce from decomposing 1.3 grams of NO2. How many molecules of oxygen? We're looking for molecules of oxygen can we get from decomposing a certain mass of NO2. If we look on our main chart, we're dealing with a mass of NO2, which would be right here. Our given is a mass of NO2, and we're trying to find molecules of something else. Well, molecules is right here. Molecules is a quantity count. So we have to go from mass to moles. That will require using a periodic table, and we'll be dividing by the mass of the substance. We'll use our balanced chemical equation to go mole to mole, where the moles of the thing we're trying to find, which is in this case molecules of oxygen, so moles of oxygen will be on top, moles of NO2 will be on the bottom, and that'll get us to right here. And to get to molecules, we'll need to multiply by Avogadro's number. So this problem is going to take 3 steps. Mass to mole, first step. Mole to mole, second step. Mole to quantity count, third step. So when we get to our answer, 3 steps. 1, 2, 3. As we saw from our chart, we're going to have to add the molar mass of NO2. Molar mass of NO2. There's 1 nitrogen in NO2 at 1401. There's 2 oxygens at NO2 at 16 each. 16 times 2 is 32. Plus 1401 will get us to 4601. And the mass will be on the bottom. Our given is 1.38 grams of NO2. That leads the problem off. Our given is 1.38 grams of NO2. That'll lead off right there. That'll lead us off. Our question is molecules of O2. There's our molecules. Question mark, molecules of O2 are 1.38 grams of NO2 is right there. And again, we're dividing by that mass. This chart will tell you to divide by that mass. Grams are on the bottom. The problem, the little help chart that we had to go along with these problems also tell you to divide. So right here, they're showing you how to add up the molar mass of NO2, and they're telling you to put that mass on the bottom. There's 1 mole of N at 1401. There's 2 moles of oxygen at 16 each, so we'd write 32 here, 1401 here, add them up, 4601, and that would go on the bottom. Right here, our first conversion, the 4601 should be on the bottom, as they've done here. So now where are we? Where are we now? We want to go mole to mole. In general, we're going to moles of oxygen, so the coefficient in the chemical equation for oxygen should be in front of moles of oxygen. What we are given should be on the bottom. That's moles of NO2, and we use the coefficients from the balanced chemical equation. This chart is showing you how to do it generally. Right here, it's more specific. Our balanced chemical equation, we'll see that it's 2 moles of O2 for every 2 moles of NO2. That's our second conversion factor right here. There's our first conversion factor. There's our second conversion factor. Where did they get the 2 and the 2? We would see that right here on our balanced chemical equation. 2 moles of NO2 for every 2 moles of O2. What we're trying to find goes on top. What we're given goes on the bottom. Let's say we don't have those charts. How would we know that? Well, in our first setup, how do we know grams are on the bottom? Because grams are right there. Whatever our givens unit is must be on the bottom, so we can factor or cancel those labels out. Dimensional analysis will tell us that if we analyze the dimensions, grams of NO2, we need it to go right here. They call it factor label because we're factoring out those labels. We now have moles of NO2 on top, so moles of NO2 must be on the bottom so that they cancel out. We're now in moles of O2. Why do we have 2's here in front of these? Because those numbers are coefficients from the balanced chemical equation. So now where are we on the general chart? The general chart, we are now right here. Moles of O2. And we're trying to get to molecules of O2, so we need to multiply by Avogadro's on top, mole on the bottom. On our actual assignment, we see that right here as well. Our equality is 1 mole of O2, 1 mole of anything, but 1 mole of O2 has 6O2 times 10 to the 23rd molecules. That needs to be on top. Right there, it's on top for us. The molecules need to be on top because that's the unit we're trying to find. Molecules of O2 on top, molecules of O2 on top. Moles of O2 will cancel with moles of O2, leaving us with the unit we want. If we fire that into our calculator, I think it comes out to 1.81 times 10 to the 22nd molecules. Our final question, how many liters of nitrogen gas would be produced through the decomposition of 3.5 liters of nitrogen dioxide? So this time they're giving us a volume, liters of nitrogen dioxide, and they're asking for how many liters of nitrogen gas would be produced. So they gave us a volume and they're asking for a volume. When we look at our master chart, they gave us a volume and they asked for a volume. We can use a shortcut. We'll see why we can use a shortcut, but we can use a shortcut to go from volume to volume. It just says put the coefficient from the chemical equation in front of the thing we're trying to find in liters, and put the coefficient of the thing we're given from the chemical equation on the bottom. Tells us right there to do that. That is a volume to volume shortcut. We'll see in a second why this shortcut works. It just says put the coefficients of the one we're trying to find on top, coefficient of the one on the bottom, and put liters after it. Let's see if that's what they did here on the sheet. Our chemical equation, 2 moles of nitrogen will produce 1 mole, or 2 moles of nitrogen dioxide will produce 1 mole of nitrogen. So it's 2 to 1. So the 2 of the thing we're given, the nitrogen dioxide, goes on the bottom, liters of nitrogen dioxide. The one we're trying to find, the question is liters of nitrogen. That goes on top, coefficient. So we have 3.5 times 1 divided by 2. That's 1.75. That's doing it in the shortcut. But why does this shortcut work? Why can we just insert the coefficients, 2 on the bottom, that's the one we're given, 1 on top, 1 liter on the top? Why does this work? If we look at the long version, we can see why this works. Let's take a look at why. We go to our chart here. There's the shortcut. But if we take the long route, we go volume to moles. When we go volume to moles, on our first setup, 22.4 is on the bottom. On our last step, we still use the balanced chemical equation to go mole to mole. But on our last step, the third step, to go from moles to volume of the thing we're trying to find, we're multiplying by 22.4. So our given, going from our given nitrogen dioxide to moles of nitrogen dioxide, we divide by 22.4. To go from moles of what we're trying to find, nitrogen, to volume of what we're trying to find, nitrogen, we're multiplying by 22.4. Let's take a look and see what happens then when we set it up. We're given 3.5 liters of nitrogen dioxide. They want liters of nitrogen. As we saw, our first step was to go 1 mole and divide by 22.4. We just saw that. First set up, divide by 22.4. Here it is. Dividing by 22.4. Then we use the coefficients from the chemical equation. We've got to use the coefficients from the chemical equation. 2 moles of nitrogen dioxide would be on the bottom for every 1 mole of nitrogen on the top. That's our mole to mole conversion. The one we're trying to find is nitrogen. It's on the bottom. The one we're given is nitrogen, or it's on the top. The one we're given is nitrogen dioxide. It's on the bottom. So now we're at moles of nitrogen. Let's look back. We're at moles of nitrogen and we're going to volume. We need 22.4 on top. We need the 22.4 on top. There it is, 22.4 on top. What happens? We have a 22.4 on the bottom here and a 22.4 on the top there. They cancel out. The only numbers we're left with are the 1 over the 2. The 1 over the 2. So you can see now why this shortcut works. When we're going from volume to volume, or for that matter, when we're going from a quantity count to a quantity count, there's a shortcut as well, because if we go from a quantity count to a quantity count, when we go from quantity count to moles, we're dividing by Avogadro. When we're going from moles back to quantity count, we're multiplying by Avogadro, which leaves us only with the coefficients as the numbers in that problem. So that shortcut works there as well. This concludes our help video on 9-19. If you have any questions beyond what we see here, don't hesitate to fire me an email to ask me those questions. We can meet. We can do whatever you want. We can do a Google Meet. We can do a Zoom. We can answer back and forth by email. We can make additional help videos, whatever you need. But thank you so much for your work on this, and hopefully these help videos cleared up any confusion you might have. Thank you again.